Okay, welcome to the lecture here. We're going to pick up on chapter 8, and we're going to lecture for just a little bit. We'll stop early, and then you can take your quiz, and then we'll have lab afterwards. Okay, so chapter 8, we're going to get into some important sort of conversions and stuff like that. Moles, grams, Avogadros number. We'll also talk about empirical formulas, molecular formulas, and stuff like that. All right. Okay, so chapter 8 is about chemical composition. I took out a couple of slides. Yeah, so that was all the naming stuff that we covered last week. So that's going to be due today. Yes. Okay. So I took out a few slides at the beginning of your handout, so we'll kind of pick up a little bit into it as well. On a balance or anything like that. So typically in sort of chemistry, when we don't have a way to maybe directly measure something, we oftentimes will come up with a standard. And the standard that they use sort of for mass is an isotope of carbon, and it was the carbon 12 isotope which they used. And basically the carbon 12 isotope, as we'll sort of see, has a mass of what is known as 12 AMU, which is an atomic mass unit. And so essentially they sort of use this carbon 12 isotope, and since it had sort of a mass of 12, they basically compared sort of all the other atoms to it and said, like, hydrogen's only about, 8% as big as perhaps the carbon 12 isotope. And then they came up with sort of a atomic mass for hydrogen of like 1.008. And that's basically, if you take about 8% of 12, you get about 1.008. So really the mass of an atom, as you may remember, has to do with really the nucleus. And inside the nucleus is where we find protons. It's also where we find neutrons. And since they are the heaviest of those three subatomic particles, if you remember, protons and neutrons are about 1,800 times each heavier than the mass of an electron. And both of those guys are found in the nucleus, and most of the mass of the atom is made up of that nucleus. So it would make sense that we sort of think about the mass of an atom as basically being made up of those really particles, those protons and those neutrons that are in there. And if we do some mass of those things, the mass of a proton is about 1.66 to the minus 24 grams. And if we do some of that mass, we get these sort of really big or very small numbers, which obviously if we're doing some calculations, they're going to be very hard to sort of continue to sort of use in calculations. So scientists sort of took that really small number that we get when we kind of add up all the protons and neutrons, and that an atom has 1.66 times 10 to the minus 24 grams, and they basically call that an atomic mass unit. And what this does is it sort of converts those super small masses that we would have for atoms into maybe a more sort of usable type unit. And so, like I said before, carbon 12 was the isotope that they used to sort of figure this out, the mass of everybody. And we have a symbol, and underneath it on the periodic table, that is where we find the atomic mass. And the atomic mass of every element you can actually find there on the periodic table. As you can see, they're not super small numbers. They are using this sort of conversion into atomic mass units. basically sort of more usable numbers rather than that really small numbers that we normally would get if we sort of added up all the protons and neutrons because of their small mass. And we can't pull that number off. So for example, if you look under hydrogen, it says 1.008. That means that there's 1.008 AMU in an atom of hydrogen. And you can basically get that relationship from anybody that you see on the periodic table. Now, you may say, well, they use, for example, oops, come back. They use carbon as a standard, and carbon-12 has a mass of 12 AMU. But if we look at the periodic table and we look underneath carbon, what we'd actually see is the number 12.01. And 12.01 is the atomic mass for carbon. So you may say, what is the difference here? So the difference is here, what we actually see here is really what is known as an average atomic mass. And it's the average atomic mass of all the naturally occurring isotopes for that element. So although most people don't necessarily call it the average atomic mass, it is just referred to usually as the average or as the atomic mass. But it really is the sort of average of all those naturally occurring isotopes. And the way that we could actually calculate atomic mass is there's sort of a formula that we could use. The atomic mass is the percentage of the first isotope times the atomic mass of the isotope plus the percentage of the second isotope times the atomic mass of that isotope. And then we kind of continue on. So perhaps if there's a third naturally occurring isotope, we would continue on in that pattern, take the percentage that it naturally occurs, sometimes called the relative abundance of those isotopes, times the atomic mass of each individual isotope. And that's really how we sort of get to those values that we see on the periodic table. So for example, taking carbon as an example of that, if we kind of look at that, let's get to a page record, right? If we look at carbon, there's kind of two naturally occurring isotopes. There's carbon-12 isotope that occurs about 98.89% of the time. And it has, again, an atomic mass of 12 AMU. There's also the carbon-13 isotope that occurs about 1.11% of the time. And it has a mass of about 13.00335 AMU. So, for example, for carbon here, these are the two sort of naturally occurring isotopes for it. And if we add up the percentages right there, we can see it comes to about 100%, which is good. If it didn't come to 100%, then we would have some other isotopes that would be missing. But here, since they do add up to 100%, we could assume that these are all the naturally occurring isotopes. So if we wanted to calculate something like the atomic mass of carbon, we would take the percentage of the first isotope, which is 98.89%, and we need to convert it into a decimal. So you could divide it by 100 or just move the decimal point 2 places to the left. We would times it by the atomic mass of that first isotope. So again, this is basically the percentage and atomic mass of the carbon-12 isotope plus the percentage of the second isotope, which is our carbon-13 isotope, and this is 0.011%, one more one, converted to a decimal, times it by 13.00335 AMU, and again, this is the percentage of the second isotope, which is carbon-13, and the atomic mass of it. And if we do that together, 0.9889 times 12, and again, we want to add it here. People always want to multiply that part, 0.0111 times 13.00335. We get 12.01 AMU. So that is the number that we see again when we look at the periodic table underneath carbon, which is that 12.01 number, and that represents the atomic mass of carbon-12. And again, it's, as you can see here, it really is an average atomic mass of all the naturally occurring isotopes. It's good to know that if you could sort of pick up a carbon atom and sort of weigh it, you would never really find a carbon atom that has a mass of 12.01. You would either find a carbon atom that has the mass of 12, like the carbon-12 isotope. You might find a carbon atom that has a mass of 13 and some change, like the carbon-13 isotope. But again, we sort of use the average value as the atomic mass. So if you had to calculate the atomic mass, again, that's sort of the formula. We take the percent times the atomic mass of the isotope plus the percent times the atomic mass of the next isotope. And again, you just continue that sort of pattern depending on how many sort of naturally occurring isotopes that you have. Any questions on sort of that calculation there? So like I said, even though natural carbon does not contain a single mass of 12.01, for our purposes and the purpose of a calculation, we do use that number as sort of the mass of carbon. Again, even though, you know, there's really no carbon with that mass, again, it's sort of an average value that we use for all those naturally occurring isotopes that occurs. So it does give you sort of a way or a conversion factor. You can pretty much take it from anybody that is on the periodic table, and you can take that number on the bottom. Usually we go to about 4 significant figures. And you can kind of do AMU per atom as sort of a conversion factor that you could get there. So iron, for example, 5585. If you looked at copper on the periodic table, is 6355 AMU per atom. And again, we could really use these as sort of conversion factors. We could use a 55 AMU per atom on top. We could also flip it around and sort of use it for a calculation where we need the atoms on top and the AMU on the bottom. So for example, here, if we wanted to calculate the mass in AMU of 431 atoms of carbon, again, we could go to the periodic table and we could get that number that's underneath. Like I just mentioned there, we basically could use it as a conversion factor here. The atoms would cancel, and that would give us how much AMU there is, which is 5176 AMU. So I want you to try to calculate the mass of 75 atoms of aluminum. And in case you don't have a periodic table near you, if you look at aluminum, it looks something like this. Okay, so looking at this again, we can basically use it as sort of a conversion factor. We could say 2698 AMU in an atom. Or again, if you needed to use it sort of the other way, an atom is 26.98 AMU. So we would just kind of do it like a dimensional analysis sort of problem. We got 75 atoms. Again, atoms are on top, so we want to get rid of them. So we're going to go with the atoms on the bottom, which is our guy on the left. And an atom is going to be 26.98 AMU. So atoms will cancel each other out. And if we multiply that, we'll end up with 23.5 AMU. In terms of sig figs, probably here 75, which is 2. So we probably should go to about here. So again, probably in this case, 2.0 times 10 to the 123 AMU. Be a good way to do that. Question on that calculation. So this is one way that we could kind of use those numbers that we see on the periodic table as the atomic mass. And one sort of unit that you could use is AMU per atom. Although, as we'll talk about here in just a second, we don't use AMU all that much after we get to kind of molar mass. We usually use it in grams per mole, as we'll talk about here in just a second. But again, that is one sort of relationship that you could get is AMU per atom. Again, for any of the elements that are on there, if you also needed to perhaps add everything together, you would just add them all together, all the parts of a formula, and that would give you your atomic mass. Any questions on that there? Okay, so atomic masses on the periodic table are not reported as whole numbers, and that is because atoms are so small, even techniques are limited. Not so much atoms are based on hydrogen. It is number or letter C here, I think. Isotopic abundance is average to provide the mass of an atom. Again, that's what we were talking about with that calculation where you take the percentage of each of those naturally occurring isotopes and you times it by the atomic mass of each one. So once you give this a go, what is the mass and AMU of 10 magnesium ions? And again, if you don't have periodic table, magnesium, little box, looks like 2431. Okay, so let's take a look. So again, here we can use this as a conversion factor over an atom. An atom is 31 AMU. So here we got 10 magnesium ions. And again, in this case, we can use that as a conversion factor. And if we do that, we can use it, even though it's atoms, in this case, ions and atoms will be the same. So we're going to go with 2431 up on top since we want AMU. And it would be the same for our ion here. Again, in order to make an ion, it will lose an electron. Remember that most of the mass of the atom is pretty much protons and neutrons, so it's the same thing really as a atom. And that will give us 243.1 AMU in this particular case. Looks like C is a winner in that particular one there. Question on that there. Okay. Now, before we go on, let's try one of those other ones just to make sure. Let's say we had, let's do this one. Let's say we had two isotopes of copper. One is copper 63, which occurs about 69.17% of the time and has a mass of 6293. And let's say the other isotope was copper 65, and it occurs about 30.83% of the time and has a mass of 64.93 AMU. Why don't you calculate what is the atomic mass in AMU? So see what you come up with on that there. Okay, so let's take a look. So again, here we have the two percentages of these isotopes. We also have the atomic mass of each individual isotope. So it's always important when you're doing sort of a problem like this that you do kind of look at the percentages. So you got 69%, you got about 30% there, 31%. So they do add up to 100%. So again, if you look at those percentages and you're not at 100%, it does mean you're missing something like, an isotope or something like that. So since we have about 100, may not always add up to perfectly 100%, maybe a little bit over, maybe a little bit under, but it definitely should be in that ballpark of about 100%. We're going to use that formula that we saw earlier, where we're going to, the atomic mass here will equal, again, we're going to take the percentage of our first isotope, and you can either divide it by 100 to convert it to a decimal, or just move the decimal point over. I'm just going to move the decimal point over to 0.6917, which is 69.17% divided by 100. We're going to times it by the atomic mass of that first isotope, which is 62.93 AMU. We're then going to add it to the next isotope. And again, sometimes people always mess this part up, like I just mentioned earlier. They always want to multiply here, but it is adding. Same thing here. We need to convert our percentage of our second isotope into a decimal. So divided by 100, or just move it 2 places to the left. Going to give us 0.3083. We're going to times it by the second isotope there, which is 6493 AMU. And if we do all that good stuff there, that is going to get us 6355. And again, usually atomic mass and stuff taken about 4 sig figs. And if you look on the periodic table there, again, underneath carbon, not carbon, copper, you will see that number, basically 63.55. So again, that is how we get to those atomic masses that we do see on the table. Any questions on getting AMU and using it as a conversion factor, calculating the atomic mass? Okay, so this brings us to sort of a new sort of conversion, and sort of in life, we have a lot of words that represent something. So for example, if we say we have a pair of something, that represents 2. We say we have a dozen of something, that represents 12. So in chemistry, we do have a name or that represents a certain amount of something, and that is actually the mole. M-O-L-E, not the furry guy, M-O-L-E. And its abbreviation for a mole is M-O-L. So this oftentimes gets people, they had to make an abbreviation somehow, so they got rid of the E. But when you see MOL, it does represent moles. It does not represent molecules, which is a very common sort of mistake that people make. They see that and they automatically think molecules, which sort of makes sense. But again, when you see that, that is the actual abbreviation for a mole. So when we talk about a mole of something, 1 mole basically represents a certain number, which is this number right here. And this number right here is 1 mole is equal to 6.022 times 10 to the 23. And when we talk about the units that go with this number, but first off, this number is what is known as Avogadros number. So when we talk about Avogadros number, it is this 6.022 times 10 to the 23. And like I said, the units that go with that can really be anything. So you could say 1 mole of 1 mole equals 6.022 times 10 to the 23. Could be particles if you're talking about particles. They could be atoms if you're talking about atoms. They could be molecules if you're talking about molecules. Really, they could be like pizzas or shoes or whatever you like. But probably most often in chemistry here, these are the 2 sort of common units that we see kind of go with Avogadro's number. Is 1 mole of anything is 6.022 times 10 to the 23 atoms, or 6.022 times 10 to the 23 molecules. That means that really you can take anybody from the periodic table. So for example, hydrogen, if I say I have 1 mole of hydrogen, that would mean I have 6.022 times 10 to the 23 atoms of hydrogen. Could also do that for 1 mole of copper is 6.022 times 10 to the 23 atoms of copper. You could also do it for things that are not just an element by itself. Say you had water, for example. Water is not an element. But you could say in 1 mole of water, there is 6.022 times 10 to the 23. And because water is a molecule, we would use units of molecules here. Same thing if you had something like 1 mole of CH4 would be 6.022 times 10 to the 23 molecules of CH4. So really what Avogadro's number is, it's really nothing more than a conversion factor. And we can basically use it like a conversion factor. We could say 6.022 times 10 to the 23 atoms or molecules or whatever the unit is over a mole. Or if you needed the moles on top, you could put the moles on top, and that 6.022 times 10 to the 23 number on the bottom, again, could be atoms, molecules, particles, whatever it is. So we use Avogadro's number really as a conversion factor to go from moles to atoms or molecules, or vice versa. If we have atoms or molecules, we could go to moles. So it really is our conversion factor really to go between those two things. And it's important because that you don't use Avogadro's number in every calculation. So it's very common. People will kind of want to use Avogadro's number in every calculation that you do. So you only want to use Avogadro's number when you're given a number that's in atoms, molecules, particles, or you're asked to solve for something that's in atoms, molecules, or particles. If there's no mention of any of those things, then you really should not be using Avogadro's number. So like I said, it's very, very common that people will kind of use it a lot and just keep using it in places where they shouldn't. So those are the sort of the key words you want to think about or look for. Is something mentioning atoms, molecules, particles, then Avogadro's number should be used somewhere along the way. Again, if it doesn't mention any of those things, you probably shouldn't use Avogadro's number there as well. Now, another important sort of relationship with that is when we do look at something, for example, on the periodic table, and we've talked about what we could use as the atomic mass in AMU per atom, but a more sort of useful unit that we oftentimes will use is what is known as molar mass. And molar mass, kind of the units of molar mass are grams per mole. It's basically how many grams there are per mole of something. So for example, we can go to the periodic table. And again, if we look at that number on the bottom, which we use for the atomic mass, we could also say that in 1 mole of hydrogen, there would be 1.008 grams of hydrogen. So we can use that relationship. Our hydrogen's molar mass is 1.008 grams per mole. And we could also do that, for example, for something that is not just something by itself, but a formula here. We would add up all the parts. So if we went to the periodic table, we have 2 hydrogens, each at 1.008 grams per mole. And we would add it to the molar mass of oxygen, which is 16 from the periodic table. So that's oxygens, that's hydrogens. And if we add all that together, we get something that's known as 18.02 grams per mole would be the molar mass of water in this particular case. Now, numerically, they are equal to each other. So numerically speaking, if you get the molar mass of a substance in grams per mole, it basically equals the same as it would for AMU per atom. So numerically speaking, they are the same. And probably 99.99% of the time, these are the units. Molar mass is typically the units that you'll use off that periodic table, unless it's specifically asked for something in AMU, which is not a very common sort of calculation. So how do all these things sort of tie together? First off, though, our molar mass is really our conversion factor to go from grams to moles, which is a very super common conversion that you have to do in chemistry a lot. and also our conversion factor to go the other way, moles back to grams. So we could use molar mass really as like a conversion factor. Again, if you're starting with grams, you would divide by the molar mass, grams on the bottom, moles on top gives you moles. If you're starting with moles, you would multiply by the molar mass, grams on top, moles on the bottom, and would give you grams. So really these last two things here, Avogadro's number and molar mass, could really be thought of as sort of conversion factors. Again, Avogadro's number, our conversion factor to go from moles to atoms or molecules. Molar mass, our conversion factor to go from grams to moles or moles to grams. How they all basically tie together is this. If I say I have 1 mole of hydrogen, that means I have 1.008 grams of hydrogen, and that would also mean I have 6.022 times 10 to the 23 atoms of hydrogen. So you could do that for, again, anybody on the periodic table. You could also do that again for things that are not by themselves on the periodic table. So for example, if I said I had 1 mole of water, that would mean 1 mole of water equals 18.02 grams of water. And that would also mean that would be 6.022 times 10 to the 23 molecules of water as well. So they're all related to each other in that sort of relationship there. That anybody from the periodic table, you can take that bottom number. And again, typically speaking, when you take that bottom number, 4 significant figures is what we use. You would take it off the periodic table from and use it in calculations. And again, that is how many moles there are in grams, how many grams there are in 1 mole. And again, 1 mole will always equal that Avogadro's number. Question on that there. And again, this is what this relationship is. And these are, sometimes you have to use both of these things together. So if you had grams and wanted to get to atoms or molecules, you would go to moles first, and then from moles to atoms or molecules. And again, the thing that allows you to sort of do that, here we use the molar mass from the periodic table. Here we would use Avogadro's number. So again, that's sort of your conversion way and sort of process in these sort of calculations. Any questions on any of that there? That also means, for example, if I took 1 mole of different substances, they may not appear to be the same amount. And that's because, for example, 1 mole of carbon, as we can see on the screen, is about 12 grams. While if I had 1 mole of chlorine, it's about 35 grams. Or if I had 1 mole of silver, it's about 108 grams. And again, they may visually appear to be at different amounts, even though they're all 1 mole, because 1 mole of each of these things does represent sort of a different amount in terms of grams. And again, may appear like this mole there's a lot more of a mole of this guy versus this guy. So again, units of molar mass are grams per mole. You can kind of think about it as like a conversion factor as well. It's always 1 mole, and the grams is always where the number stays with. So the number always stays with the grams. The mole part is always 1. And something I'll talk about now, we'll probably talk about again when we get there. But for example, if you had an equation where you had something like 4H2O plus whatever else is in the equation, if you needed the molar mass of water, you only take into account the formula. So it's only the formula when you have to get the molar mass of something. And again, that's a very common mistake as well. People see coefficients and balanced equation, and they incorporate that into the molar mass. So it doesn't matter, for example, in an equation, if there's a big number in front of it or something like that, if you're asked to calculate the molar mass of it, it is always just based off of the formula. Any questions on that there? Okay. So what we're going to do is we're going to stop there for today. So let me just clear up everything so everybody's on the same page. All right. So we are going to take the quiz. Quiz, again, as we talked about last week, is going to be on pretty much all of the bonding stuff. So the quiz will open up about 11:30. Again, you need to take it using the proctorial and all that stuff. You take the quiz. You have until maybe 12ish or so, right, to finish it. Remember, you need to start it around when it opens at 11:30. If you start any later than that, then the computer will cut you off and you won't get any more time. So make sure you do start it around 11:30. Since we're going to take the quiz and give you a chance to kind of stretch after that and all that good stuff, we will start lab later today. Lab will start at 12:20. We are going to do experiment 12 today, which is, I think, the hydrate experiment. As I mentioned last week, I misspoke earlier. So as I mentioned last week, activity 10 and 11 are due not today, but they are going to be due at the end of lab on Wednesday. So those need to be turned in on Wednesday, as I think of what I mentioned last week. So I did misspeak. So at the end of Wednesday, those guys are going to be due. Again, you should have been able to start working on those already since we finished talking about naming last week. So you should be able to knock those out. But we are going to continue on with the lab that is scheduled for today, which is 12. And we'll go over that, and I'll let you know when that will be due as well when we get there. Any questions on any of that? A reminder as well, we are now getting back into real labs, I guess I'll quote it. Well, real lab, not so much activities and stuff like that. So again, the online pre-labs are again going to be due the day of the experiment. So make sure again that you do not miss any of those things. Yes, so starting now on, like we've done before, you will have pre-labs like we had before. So again, in case there was some confusion on that, if you didn't get your pre-lab in today, I'll open it back up. You could get it in on, by Wednesday. But starting today and then Wednesday as well, we will have the pre-lab for 13 that you need to have done as well. And like normal, now for the rest of the time, there really is no more kind of activity type experience, I don't think. So they will all have pre-labs. They will all be due. And also don't forget the Cengage pre-labs, so the online pre-labs as well. All right. I think I got everybody's question, I hope. All right. So remember on the quiz, you will be given a periodic table. You will need to upload some work on that. You'll also be given, I think, maybe some electronegativity values up there as well to use on the quiz. So make sure that you do upload it immediately after you submit the quiz. And like I said, we will start lab at 12:20. We'll be doing experiment 12. And again, make sure that you start the quiz around 11:30 when it opens. Otherwise, again, it will cut you off if you start too late and you won't get the full time available. All right, any other questions on anything? All right, good luck on your quiz. I'll see everybody in about an hour when you're done. Again, you don't have to log into the lab Zoom meeting for your quiz, but afterwards at 12:20, log into the lab meeting. All right, good luck. I'll see you in a bit. Make sure you put here if you haven't done so.